All right, on to the next one. Let's do 2-11 in the book. And this one's somewhat similar to the 2-9. Oops, should have rotated back. 2-9 in the book that we already did. The only difference is this one you actually do need to solve it all the way out. Sorry, I'm jumping around here. I'm just trying to find the problem. Here we go. Here we go. 2-11. So we've got a sealed container, 25 pounds of propane, 350 psi, and its volume's 3 cubic feet. Weights and volumes are the two phases in the container. So let's make believe for a minute here. We got some container, you have liquid, you have gas on top like that. The volume of this guy is 3 cubic feet. And what else did we say in the problem description? P is equal to 350 psi. And what else? We know that it's the mass equals 25 pounds, and this is propane. So we want to calculate the weight and volume of both liquid and gas in this situation. So if we go back to our previous problems, first of all, let's take a look at the Cox chart and figure out this for a second. So we go back to our Cox chart, and here, this is the book. Actually, let me get the digital one up. If we go back to the Cox chart here, and where are we at? Blah, 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 blah. So here's our Cox chart. We're looking at propane, and propane is right here. I can rotate this back. So here's the propane line, and we're saying it is at 350 psi. So here's 350 propane right in here. So for there to be both liquid and gas in the system, we would have to be at a temperature of 150 Fahrenheit because it's laying on the vapor pressure line in Cox chart. So let's see. So I've written that down for you here. That's just an assumption because he told you there's liquid and gas. We can calculate that out here in a minute without even needing to know whether or not there is. We'll find it out one way or the other. So if you remember, for calculating this earlier, we had this equation that is volume liquid, density liquid plus volume gas, density gas. That should equal our total volume, which is 3 cubic feet, correct? And then we have to satisfy this equation, volume of liquid plus volume of gas. I'll just keep it the same, equals, oh, I'm sorry, this is wrong. This is the 3 feet, and this is 25 pounds. Sorry about that. So we already know this, and we know we need to solve these equations. So we can pick one. Let's turn it volume liquid equals 3 minus volume gas. And we can take that and substitute that into this equation. So then we would have 3 minus volume of gas times density liquid plus volume gas, density gas equals to 25. So now we need to find these values. If you remember from previously, we can do it that really bad method by finding it on that density chart that looked like this shape from the book. That's not really a good way to do it. So I'm going to find it in my NIST properties. So let's bring NIST over here, and let's get this out of the way. So here's NIST properties, and I got to pick. So we're looking at propane this time, propane, and I'll look at Fahrenheit, PSI. Okay, isothermal properties. Oh, I want to change this to pounds per cubic foot so that I know what I'm doing. So click that, enter a temperature. So we already know it's 150. P low, I can do the P low to be whatever, 330, because I already saw it sitting on that Cox line at around 350. And I can make this 0.1. Let's get our data. So here's our data. So here's the plot we got earlier. And you can see here's the actual vapor pressure is right at 343.7. So let me drag this back in here. So we can see this value we're reading off the other Cox chart is kind of crappy. So it's really 343.7 is our real value. That just shows you the accuracy of Cox charts. And now this is giving us the density of our liquid phase or vapor phase, which is rho G. So our rho G is going to be equal to 3.5581 VG. It's going to equal to 25 eventually. And then here's our liquid phase. So we're looking at 3 minus VG times 25.912. That is our liquid phase. So now we want to solve this. So here's what we're trying to solve for. We've got our densities in there now. So we basically want to get 3 times this 25.912. That would be, let's say, minus 25. And then we're going to get that equal to 25.912 minus 3.558 V sub G. So our V sub G is going to be this ratio of 3 times 25.912 minus 25 divided by, we'll do that just to show it clear, 25.912 minus 3.5581. So V sub G, let's bang this out on the calculator, times 25.912 minus 25. It's going to equal to 52.736. Let's divide that by the other. So 25.2 minus 3.5581. That is going to equal to 22.54. The volume of gas is 2.359 cubic feet. And so then we want to know the volume of liquid. We can come right back to this equation, and it is 3 minus 0.359, which is going to be equal to, that's going to be equal to 0.64, let's just say 641 cubic feet at that point. Now we want to know the weights. So the weight or mass of the gas is equal to Vg times rho G. So we know rho G is this value. So we can do 2.59 times 3.5581. That's going to give us a value of 59, 3.5581. That is going to give us a value of 8.39 pounds, correct? And then we know that it's 25 pounds, so the mass of liquid should equal to 25 minus this. So 16.606 pounds, but we can double check that by doing VL times rho L. Oops, that should be 0.641 times density of L, oops, is 25.912. 912 times 0.641 equals to 16.609. See the rounding error in there? So anyway, that's good enough. So here's our masses of gas and liquid. Here's our volumes of gas and liquid. That's the answers to this question.